Module A1, Objective 6, Chemical Reactions. Know the basic mechanism behind decomposition, synthesis, and exchange reactions. Give examples of each. At the end of Module A, Objective 1, I gave a challenge to balance an equation. The equation was CO2 plus H2O yields C6H12O6 plus O2. In short, CO2 is carbon dioxide, H2O is water. Those are the reactants. C6H12O6 is glucose, which is one of the products, and oxygen. This equation is the equation for photosynthesis. And while you might not think photosynthesis applies to the study of anatomy and physiology, it does, because it's through the process of photosynthesis that we get the energy that we need to survive. The easiest way to balance the equation is to start with something that only occurs in one place on the reactant side and one place on the product side. The best choice is right here with carbon. There are 6 carbon on the reactant side. To get 6 carbon on the product side, we add a 6 in front of, when we add the 6 in front of the carbon dioxide, we have 6 carbons on the reactant side and 6 carbons on the product side. Next, let's look at hydrogen. It only occurs in one of the products and in one of the reactants. To get 12 hydrogens, we add a 6 in front of H2O. 6 times 2 is 12. We have now balanced our hydrogens. Last but not least, let's look at oxygen. Oxygens are a little harder because they occur in 2 molecules on one side and 2 molecules on the other side. To figure out how many oxygens we have, you multiply 6 times 2, which is 12 in carbon dioxide, plus 6 times 1, which makes 6 in water. To balance that, we have currently 6 plus 2, which is only 8. Now, the mistake many people make is to add, they think, I only need 10 more. So they add to just the oxygen, they add a 5. But when you add a 5 in front of the oxygen, that only gives you 16. You have to remember you have those 6 there in the glucose molecule. So what you need is to take the 18 from this side, subtract the 6 that are already occurring in the glucose molecule, and that leaves 12 more that we have to account for in the oxygen. To get 12 out of oxygen, we have 6 molecules of oxygen. We have 12 oxygen atoms, and now our equation is balanced. I hope you all got it right. Let's talk a little bit about energy. Energy is an important part of our study of anatomy and physiology. Energy is the power to do work. And work is a change in mass or distance. There are 2 forms of energy. The energy of motion, which is called kinetic energy, and the energy that is stored energy, which is called potential energy. We are dealing with both types of energy. And it's constantly being changed from one form into another, from kinetic to potential and potential to kinetic. One of my favorite examples of energy is Jack and Jill. Everybody knows and understands the story of Jack and Jill. Jack and Jill went up the hill to fetch a pail of water. Right? To get up the hill, Jack and Jill were doing work. If you've ever climbed a hill, you know it's work. So they were expending energy. They were using that energy to power up the hill. That energy is kinetic energy, the energy of motion, the energy that's actually doing work. Now, when Jack and Jill, there's Jack, and here's Jill. When Jack and Jill got to the top of the hill, what happened? Well, while they're at the top of the hill, they have a good deal of potential energy. That's stored energy. It was stored, and it has to do with their position when they reach the top of the hill. But the rest of the story goes is that Jack did what? He fell down the hill. That also was kinetic energy, energy of motion. And then what did Jill do? She came tumbling after. That also was kinetic energy. So kinetic energy gets you up the hill, and kinetic energy gets you down the hill, and at the top of the hill you have potential energy. Now, the reason why this is important is because our bodies are constantly in motion. That's one of the things that living things all have in common, is movement, and the ability to move things within our bodies, move our bodies around. That all takes energy. And that energy has to come from someplace, and it comes from the foods that we eat. And it's stored in the foods that we eat from that process. Remember just the slide before when we talked about photosynthesis? The food that we eat ultimately comes from the process of photosynthesis. Energy from the sun, kinetic energy from the sun, is utilized by the plants to make chemicals that we eat, and we can derive our energy from the chemicals in our food. Chemical energy is a major source of potential energy, stored energy in chemical bonds. And that's why we study chemistry and why we study different types of energy and see how they apply to living systems. In a chemical reaction, there are two parts. We've already looked at this. Reactants, which are the materials going into the reaction. And remember, they're usually on the left-hand side. Reactants. I'll just put an R. And then on the right-hand side, we have the products. And it really is either reactants or reactant, and products or products. Metabolism is the sum of all chemical reactions that occur within our bodies. And there are different types of chemical reactions, which we're going to talk about in this objective. Decomposition reaction, also called catabolism, breaks chemical bonds. In the example given here, AB represents a chemical with two parts, part A and part B. A and B don't represent elements, so those aren't chemical symbols. Those are just letters used to represent a portion of a molecule, a portion of a compound. In a decomposition reaction or catabolism reaction, AB yields A plus B. An example of a catabolic reaction is hydrolysis. Now, hydrolysis is interesting because you can see a root word in there. The root word being hydro. Hydro means what? Hydro means water. Water is going to be involved in a hydrolysis reaction. And right here you can see, lo and behold, there's water. In a catabolic reaction, specifically hydrolysis, the term lyse means to cut or break. So in a hydrolysis reaction, we're going to utilize water to break a chemical bond. When that happens, if you look at the picture here, we have the reactants and we have the products, just like before. Somewhere right in here is a covalent bond that is going to be broken. And there's also covalent bonds, if you remember what water looks like. An oxygen with two hydrogens. That one of those covalent bonds is going to break. And a portion, an OH, from one part of that water molecule is going to get attached to one of the products, and the hydrogen from that water molecule is going to get attached to the other. And that's the way we break a chemical through hydrolysis in a decomposition reaction. A synthesis reaction is similar, it's kind of like the opposite of the decomposition reaction. Synthesis reaction is called anabolism. Now, many of you have heard of anabolic steroids. And what do anabolic steroids do? They build up the body. So an anabolic reaction or a synthesis reaction is going to form chemical bonds that's going to produce larger molecules. The form of an anabolic or synthesis type reaction is A plus B yields AB. Common term is dehydration synthesis. And there we see that base word again, that hydration, the hydro part, which refers to water. The term I like here, the synthesis, reminds you that you're synthesizing something, you're making something larger. This is also called a condensation reaction because in the process of this reaction, water is formed. So if you think of condensation on a glass, water forming on a glass, but water is formed during this process. And you hopefully notice here that what we have is ABC, and this H is actually representing a hydrogen atom, an OH representing the OH group. Those two come off and form water. When those two are removed, a new covalent bond forms between the ABC portion of the molecule and the DE portion. So we have a new product, A, B, C, D, E. This will become more apparent when we start to talk about organic chemistry and building large molecules from the elements that we've been talking about so far. In an exchange reaction, it involves basically two pieces. First, we have decomposition and then synthesis. First, we have to take apart A and B, and we have to take apart C and D. The A portion is going to bind with the D portion to produce AD, and the C portion is going to bond with the B portion to produce CB. Reversible reactions are reactions that can occur simultaneously in both directions. So while AB is being formed, It's also decomposing into A and B. At equilibrium, the amounts of chemicals do not change, even though the reactions are still occurring, meaning they're occurring as quickly in this direction as they are in this direction. Reversible reactions seek equilibrium, balancing opposing reaction rates. If you add or remove reactants, the reaction rates will adjust to reach a new equilibrium. When we're dealing with chemical reactions, another thing we have to keep in mind is whether these reactions are exergonic or endergonic. The term ergonic that you see in both endergonic and exergonic refers to ergon means work. So exergonic and endergonic refer to work. Ex, if you think of an exit, means out, and end means in. So exergonic means work out, endergonic work in. Exergonic reactions produce energy, and endergonic reactions use energy. Both types of reactions, whether they're exergonic or endergonic, require a little bit of energy to get started, and that is called energy of activation, also called activation energy. Let's say you're going to start a fire. And for a fire, you need a few things. You need a fuel source, you need oxygen, and there's something else that you need. And that something else you need is a spark. You need a little bit of fire to start that fire out. Whether a chemical reaction is endergonic or exergonic, it's going to need a little bit of energy to start that process along. Even in an exergonic reaction like a fire, we need an activation energy or energy of activation, and that would be this spark. That is a limiting factor of most chemical reactions. And our body works to get chemical reactions going by aiding that spark. And it aids the spark through enzymes. Enzymes are, for the most part, proteins in our bodies. One of many different kinds of proteins, but they have a very specific process, a very specific function, and that is to lower activation energy in reactions. Again, activation energy is that amount of energy needed to get a reaction started. The enzymes are going to lower that energy of activation. We give them a specific name, and that is that they are biological catalysts. A catalyst is a chemical that increases the speed of a reaction without being changed in the reaction, and it is not considered to be a reactant. This is a figure from your textbook, figure 2-7, that shows the amount of energy required for activation of a chemical reaction, with and without an enzyme. If you look at it, look at the amount of energy from here all the way up to here that should be absorbed or needs to be absorbed by the reactants for that chemical reaction to take place without an enzyme. But with an enzyme, it takes much, much less energy, because energy is in short supply. Our bodies have to compensate and have to be conservative in how they use energy. And enzymes help the body to continue to have chemical reactions, but meanwhile conserve energy. We will be talking about enzymes, chemical reactions, building molecules, breaking down molecules, and how energy is used throughout the semester.